Hello everyone, I'm going to give you the whole briefing of chapter 7. We go to 7.1, gravitational force and field strength. The equation is F equals to gmm over r squared. And then we also have gravitational field strength, that is Ag equals to gm over r squared. For the gravitational potential energy, the equation is U equals to gmm over r. Now I want to focus on 7.3. Here we have to know how to derive the escape velocity like this. And then we also have to be able to derive the velocity of a satellite, v equals to surd gm over r. Here is the direction of the velocity, always tangential to the circular motion. And we also have to know how to derive the period of a satellite that's orbiting the planet like this. Other than that, we also have constants. We have g, mass of the Earth, and radius of the Earth. Let's discuss question number 5. The gravitational field strength on the Earth's surface is 9.8 Newton per kilograms. So we're going to do the listing straight away. But why is the unit Newton per kilograms? You know what? Let's do some dimensional analysis a little bit. We have Newton, which is equal to kilogram meter per second per second. So the acceleration is Newton per kilogram, so kilogram meter per second per kilogram. So we cancel out the kilograms. Yes, we get meter per second per second. So it's correct lah. So the question wants us to determine the gravitational field strength at point X at a distance 2.5 r from above the surface of the Earth, where r represents the radius of the Earth. If you remember our soalan assessment kuliah, I've asked you how to calculate small r. So r is actually capital R plus h. So total up is 3.5 r, and that gives us the total r is 2.24 times 10 to the 7th meter. Now let's do some calculation. A equals to gm over r squared. So we do substitute all the values like this, and our acceleration is 0.795 meter per second per second. Let's go to question number 8. A mass is moved from the surface of the Earth to a height h, where the height is way smaller than the capital R, and that is the radius of the Earth. Show that the change in the gravitational potential energy of the mass is mgh, where the g is the acceleration of the free fall. I want to list down these equations because we're going to need them in deriving this u equals to mgh. So we have r equals to capital R plus h, we have g equals to gm over capital R squared, and we also have u equals to negative gm over r, small r. Let's zoom in on this Earth. Okay, this is you, my dear. Try to jump from the surface of the Earth. The height is h, small h, and the radius of the Earth is capital R. Hence our initial length r is radius of the Earth, which is r, capital R, and the final length r equals to r plus h. Difference in gravitational potential energy delta u equals to u final minus u initial. G times capital M, M is the mass of the Earth, small m is your mass. The final small r is capital R plus h minus negative gmm over, well, our r, capital R, equals to, I'm factorizing the negative gmm, times 1 over r plus h minus 1 over r, and then kita samakan dia punya denominator, kita darab silang. So dia jadi r tolak r campur h bahagi dengan r squared plus rh. So we cancel out the r yang sebelah atas tu. So kita dapat negative gmm darab dengan negative h over r squared plus rh. But since the value of h is way smaller than the capital R, h ni yang height yang korang jumping tadi tu, lepas tu the r is the radius of the Earth, so big kan, it means that the rh is way even smaller than the capital R squared. So we can ignore the value of h and rh as it is too small to make any significant change to the gravitational potential energy. Hence our new delta u equals to gmm times h over r squared. Okay, jom kita rearrange. Kita ada delta u sama dengan m, lepas tu saya letak dalam kurungan gm over r squared kali dengan h. Gm over r squared, kalau kita tengok dekat sebelah atas, sama dengan g. So bila kita gantikan balik, dia akan dapat mgh. Proven! Yay! Question 14a, derive the period of the satellite motion. We have omega sama dengan 2 pi over t, and also we have omega equals to v over r. We're going to combine these two, so it becomes 2 pi over t equals to vr. I'm rearranging t bawa ni atas, r bawa ni atas. So our period t equals to 2 pi r over v. And we know that v equals to sert gm over r, right? So it's actually sert gm over sert r. So I'm going to put it back in, the v in this equation. Tapi sebabkan v dekat bawah, so saya terbalikkan lah. 2 pi r kali dengan sert r over sert gm. So saya squared kan sebab nak buang the sert. So t squared equals to 4 pi squared r squared times r gm. So kita akan dapat t squared equals to 4 pi squared r cube over gm. Dan kita neutralize balik, kita neutralize, so dia akan jadi 2 pi over sert r cube over gm, derived. Let's go to question B, 14b. The period of the satellite of the Earth is t, and its radius of the orbit is r. What is the relationship between the r and the t? So here, kita kena letak variables. Apa variables? So we have t, which is the period, and the r, which is the height. So the equation is t equals to 2 pi sert r cube over gm. So what's the relationship? They are directly proportional. T is direct proportional to sert r cube. And let's go to question number 15. 15a. Explain why satellite is capable to orbit the Earth. The centripetal force required for the circular orbit of the satellite around the Earth is provided by the gravitational force of the Earth on the satellite. So in other words, mass of the satellite is useless. Tak kisahlah dia berat mana pun, dia ringan ke apa ke, it doesn't matter, because the satellite is capable of orbiting the Earth because of the gravitational acceleration or the gravitational force of the Earth itself. Alright, let's go to question 15b. The period of a satellite is equal to the Earth rotation. In other words, 24 jam lah. And then calculate in terms of the radius r besar, the height of the satellite above the equator. Apa nak buat ni? First of all, kita tukar dulu. Because we know that the period is 24 hours, right? We change it to SI unit, which is in second. So it becomes 86,400 second. The question is looking for the height of a satellite in terms of r. So h sama dengan berapa r? Tadi saya dah ajar r sama dengan r besar campur h. When we rearrange, it becomes h equals to r kecil minus r besar. And now let's find the small r first. The only place that we can get small r dan ada masa, period, is t equals to 2 pi sert r cube over gm. Kita buang sert dengan cara squarekan period kita. So t squared equals to 4 pi squared times r cube over gm. And when we rearrange, kita dapat r cube equals to t squared gm over 4 pi squared. So we rearrange and we get our r equals to sert cube gmt squared over 4 pi squared. And then at this stage, it's quite easy dah. Kita substitute all the values and finally we get our r, small r, 4.225 times 10 to the 7th meters. But this is not the final answer because the question is asking for the height in terms of r. But first, let's get the value of the h itself. R minus capital R. And the final answer is 35.85 times 10 to the 6th meter. So in terms of r, kita kena bahagikan dengan the radius of the Earth itself. And our final answer is 5.6 r.